I will talk about some general topics, but also will show some of our latest research results. So the topic of the conference was focused on how we can accelerate quantum chemical research using machine learning. And we've got many exciting examples from different areas of this field and also from different regions of our planet. And our research is also focused on different areas in machine learning applications to quantum chemical research. What I want to emphasize during this talk is that we use and try to develop machine learning methods for practical computational chemistry. So we try to do black box implementations and something that you can easily use without even knowledge much of machine learning. Our group, I will just briefly introduce here. So this is from one of the hiking, and we need to update this picture with more group members. And we do our machine learning implementation and simulations with the MLatom package, which is connected also to research devoted to electronic structure calculations. And since we do practical research, we want to do big systems and fast simulations, something that you can even run on single CPU. And this is only possible if you use either machine learning or some empirical methods or combination of them. So why do we use machine learning? As you know from this conference, is because it's much faster than quantum chemistry. And it's not the end of the story. It's not just faster, but it allows you to improve your quantum mechanical methods by different ways. So one of the interesting ways is to improve your Hamiltonian, and we see some examples in this conference. And also you can use machine learning to learn wave function, and then use this wave function to get properties. On the other hand, what most of people do, and what we also do, is calculating properties predicted by quantum chemistry, and not just quantum chemistry, also properties that you cannot calculate even with quantum mechanical packages, but some experimental properties. And then we can use machine learning for direct prediction of the properties. So these are basically three big areas where machine learning can be used, and it basically covers all applications we saw in this conference and that are in literature. Another way to look into it is that if we discuss how to improve accuracy of our methods, is that actually if you try to improve even slightly accuracy, the cost rises exponentially. So if it takes even for small improvements like 0.1 kcal per mole or 0.5 kcal per mole, you really need to greatly increase the time you spend. And that's why accuracy can be achieved with very elaborate ab initio methods, but time, so the cost prohibits to do it. With machine learning, basically it's a game changer because we can run very fast calculations at the accuracy of target approach, even a couple cluster or full CI for very small systems. And this is at the cost slightly above molecular mechanics. Other way to do it is to combine methods together, and I will show at the end of the talk very exciting approach how we can do it in a very general way and achieve very high accuracy and good transferability. Now, everyone knows that machine learning potentials is one of the most broad fields of applications and the most intensive field. And there are many of them. I'm not going to cover all of them, but I want to just discuss some general topics which we should take into account when we try to use or develop our own potentials. We have thousands of potentials, I guess, and we can develop basically infinite number of potentials by changing different parameters, like choosing different descriptors, tuning your even the same descriptor with different modifications, and you can also choose different algorithm, and within the same algorithm you have also hyperparameters. So basically there is infinite number of combinations, and you can publish every month a new machine learning potentials. But they all can be more or less divided into big classes, and one of them is kernel methods, other neural networks. There are also linear methods not shown here, but these are the most popular. And so you can do that using global descriptors, so describing the whole molecule. We saw some talks about these. Very popular and very powerful approaches to describe it as local descriptors, which allows you to decompose the energy, for example, into atomic contributions, and then you can sum up. This allows you to train your system on small molecules and then apply to big molecules. And this class of kernel methods and global descriptors can be extremely simple. This is our model, which we call KREG model. And in this KREG model, it has a descriptor includes all inverse distances in the molecule, so extremely simple descriptor. And calculations are performed by this regression, or you can look simply about it as a basis function extension. So it's very easy for us quantum chemists to understand what it does, extremely easy to implement, very fast. And the question is, now we have all these different models. Do we need more models? And which model to choose, right? And here, also before I discuss some conclusions, I would like to emphasize that we need some standards already in machine learning quantum chemistry, because quantum chemistry has already standards. If you look at the papers in quantum chemistry or computational chemistry, you go into the method section, and they say that we use B3LEAP 641G star, you already know what they're using. They're using DFT functional, B3LEAP with this basis set, so you already understand the method. With machine learning papers, unfortunately, the situation is much more complicated, because if you look at the papers, you really need to sometimes have time to understand what was actually done. I suggest that also in the method section, we provide very, very brief descriptions, what we done, what is our input, what is our descriptor, right? What is our output, what is our algorithm, and in very, very short format, and what is our data used. And now something else. So it seems we already kind of in a very rapidly maturing field, and many things already matured to the level that you can use them out of the box. But still, there are some inconsistencies in the manuscript, even for the same and simple concepts. For example, if you say we have two models and we want to compare two models trained on 100 points, and try to decide which one to use. And one model gives you 4.45 kcal per mole error, and another 3.90. So should we use this one, which gives a smaller error, right? But before we even go there, what does it mean, 100 training points? It's not obvious. It seems that it should be obvious because it's just training set. But no, in the papers, you really need to very carefully check what the authors meant by training points. Very often, validation set, which was used for indirect training, for choosing hyperparameters of your model, was not included in the training set. It means that basically these points were not accounted for, but for this validation set, you still need to generate a very expensive, sometimes very expensive reference data. And in principle, the validation set should be included in the training set. And that's what many people use. And if you don't include validation set in the training set, then you have sometimes trouble to define in the paper what you're actually doing. I saw sentences in the papers when people write that we divided training set into the training set and validation set. Well, you cannot divide training set into the training set and something else. It's just exclusive. So much simpler approach for us would be just to call that we have subtraining set, which is used for example, training your neural network, and validation set to choose hyperparameters. And that would be a very systematic way to do it, and very easy for us to understand what is done. Another point is that it's not the end of the story. Yeah, you trained it on 100 points, you choose a new model, but then your data increases when you generate more data. For example, via active learning, you add more points to your database, and suddenly the other model becomes more accurate. So what happened? And what happened is very simple. If you increase the number of training points, different models have different speed how they improve. This is what is called learning curves, and this is something when you do development of a new method, when you do comparison of different methods, you should always show that how different approaches compare to each other when you increase the number of training sets, and then you understand that if you expect more training points, then one model can become better than the others. And at some point they cross, so they have basically the same accuracy. Here we benchmarked lots of machine learning potentials, which are very popular, and you already know many of them. DeepMD is very popular. FizNet is also very well known. ANI is, we had the first talk about it. GAPSolve also is very widely used. So all this, like this is Coulomb matrix, which is considered outdated, but it actually outperforms many of the new methods, like more complicated FizNet. And that is another great point, that actually you don't always need very complicated models to achieve your results. This will be the topic and the themes that you will see later also in the talk. And another thing is timing. Yeah, we can learn everything with our machine learning if we have enough data and if we spend lots of time trying to do it. The question is it worth doing it? In many cases, training a very good model will take you more human and computational resources than actually running pure quantum mechanical simulations. And one of the problems is that many methods are very accurate, but they're extremely slow to train, especially neural networks. Although believe is that kernel methods are slow, but that's not true if you want to achieve high accuracy with, for example, training on small number of points, and their kernel methods are much faster and more accurate. So you can achieve better accuracy with smaller number of points, and then you don't need neural networks. On the other hand, some level of accuracy require more data, training data, and then neural networks beat kernel methods. So basically, when you compare this all together, the timing, the accuracy, all this in a balanced way, then you see that kernel methods basically is the best choice if you have not very big training sets. And one point which I didn't mention explicitly is that if you input forces, you can improve greatly the accuracy of your machine learning model. And if you include forces for small training sets, again, kernel methods are more accurate and faster than neural networks. But if you get to larger training sets, then you do need some approximations in kernel methods. You can also make them faster, but from practical perspective, it will be probably much easier just to use neural network. The boundaries are here not strict, but this is a general guideline. Now we did this, as I mentioned, we do everything in a black box manner so that you can download our code and not just reproduce, but actually use for your own simulations. And you can reproduce all these curves and test your different models for your data set, because each data set you need to test your model. It's like with DFT, you need to benchmark your model before you apply it. And our code allows to do it basically automatically. You can replace, just choose the model you need, and then you will get the result. Now, I was mentioning that sometimes you don't need very complicated models. Later, I will show you complicated models and where you need them. But in many cases, very simple models can give you very accurate results, and they're easy to train, and that's all you need. So this KREG model, which I showed you before, is extremely simple and fast to train. Of course, it can become a bit more complicated if you try to include some more physical information, like permutational invariance of atoms. But before we go to that, another point about machine learning is that it's excellent for interpolation. The problem with chemical applications of machine learning is that we deal usually with high-dimensional spaces, and there we don't know we cannot always ensure that we interpolate. And if your machine learning model doesn't have the patterns, all the patterns in the training set, for example, if you train only these points on dissociation curve of H2, then it will not know that there is a potential well, which is very well known that like for any quantum chemist there is a well, but machine learning doesn't know it if you don't provide this information. And to do it in high-dimensional space, you can do it by using this kind of structure-based sampling, where you select different points as far apart as possible. And if you know your space from which you select training points and do it in this more or less clever way, rather than random way, you can use much less points, like here in this example, 5 times less points than with random sampling, and get even more accurate model. So with these simple models, you can also combine like delta machine learnings together. You can achieve extremely accurate results, and you don't need any neural network here. And this is very simple approach, very fast to train. And you can apply this simple approach even for more complicated applications, like learning absorption spectra, predicting absorption spectra. And here, if you do it using a clear ensemble approach by calculating spectra from many single point calculations, excited state calculations on different geometries, then you can get the spectrum by this convolution, and then you see that machine learning can be used by interpolating between these points, and you can learn excitation energies, oscillator strengths, and very encouragingly, you don't need too many points. And machine learning, in contrast to traditional approaches, provides you also additional information, such as the error estimate, and then you can use this error estimates to converge to estimate where you can stop already your generating of new reference data. And this allows you to use, for example, only 100 points, while with quantum chemical methods you need thousands of points usually to get very, very precise spectrum. And this is again implemented in black box manner, so you can already apply it. You don't need to implement anything. So one of the mottos is that the simpler the better. So simpler sometimes very often is better. And one important thing is that machine learning is often more accurate with respect to reference quantum chemical levels than quantum chemical methods with respect to the truth. So you really don't need to spend all your time trying to squeeze the last digits in your RMSE error of machine learning if your reference method is just has a much bigger error to the experiment. If you take the TD-DFT, for example, calculations of the spectrum, you see that the TD-DFT is much worse with respect to experimental spectrum than your machine learning method, which is approximation basically to quantum chemistry. So why do we need to care about some small error accuracy gains if we cover most of the error anyway by training the model and making it faster? So I was saying that it's time, so that our field is already maturing very fast, and there is a time for proof of principle. In many respects, we still need to develop many models, so the field is not closed for development. And one of the examples of proof of principle approaches was improvement of different quantum mechanical methods, and we published series of studies on this. One of these is delta machine learning. And when I was thinking about it, I saw that machine learning back then, 2013, when we started this, had a massive problem with extrapolation and massive problem with unphysical behavior. There were some errors in optimization energies, like more than 400 pK per mole. So rational solution was basically to predict the corrections to the physically correct models, like even small basis set and Hartree fork instead of full CI for H2 dissociation gives you physically correct behavior, while machine learning is more accurate but doesn't have correct physical behavior. If you combine them two and just correct this, you will get correct physical behavior and at the same time good accuracy. And we did this for many other molecules. That was proof of principle. Now, another proof of principle was that we can improve some empirical Hamiltonian itself and then use it to make more accurate predictions. That led to breaking the barrier of just reparametrizing some empirical methods, because reparametrization will not give you a better accuracy after some time you just stop improving your model. With machine learning, you don't have this limitation. And so there is time for proof of principle, and now it is time for practical usage of machine learning. We are already at the stage that then we can use it for practical applications, and that's what we are already doing. And one of the methods I'm very happy about is this artificial intelligence enhanced quantum chemical method 1, which is we call AIKM1, and it is very accurate, highly transferable, machine learning improved quantum chemical method. What I mean by highly accurate is that we achieve couple cluster accuracy, and at the speed of some empirical quantum mechanical methods, and with the transferability of quantum chemical methods, because if you train your potential, machine learning potential only on ground state properties, it will only work for ground state properties and only for the neutral molecules if you train to neutral molecules. But our approach can be applied for excited states and charged species, any species. And if you could, for example, take C60 molecule and calculate it with couple cluster single points, it will take you 70 hours on 15 CPUs, while optimizing this molecule will take you 30 minutes on 32 CPUs. With our method, you get couple cluster basically accuracy, and the speed for this molecule is 14 seconds in one CPU full optimization, without any optimization of the code, basically. And how this method is constructed is it has three components. It has a very accurate semi-empirical Hamiltonian, which makes it fast but also accurate. You have very good model, neural network model to correct ground state potential, and you have dispersion interactions which allow you to use this model for big systems where non-covalent interactions are important. And how we trained this model is that we took almost 5 million data points, energies plus forces calculated at DFT level. We trained on the difference to semi-empirical predictions, and then we did transfer learning to get the couple cluster accuracy for data set with half a million points. If you add them back, all these corrections to together, then you will get a KREG. And this is a scary table, but you only need to understand that the green is good, the red is bad. So the couple cluster is all green, so it's a good method. We all know that couple cluster is good. But it's not applicable for many applications because it's too expensive. For example, calculating hits of formation requires you frequency calculations and geometry optimizations for big molecules are just unfeasible. And red means it's bad, and you see that DFT, in contrast to AIKM1, is even worse, even very popular function. So if you have, and now I will just decompose a bit this to the different properties. So this is just focusing on ground state properties and closed shell species, and you see that AIKM1, so the column next to couple cluster, is really very, very good. And if you go to geometry optimizations, we can get for many molecules basically the same accuracy as you would expect from couple clusters. The geometries are very close to experiment. Again, very, very fast. If you take neural network potentials, they will fail this molecule because they will not describe the conjugation very well. So the bond length will be the same, which is not correct. And so AIKM1 is better than DFT. Like general DFT, because of course there is exact DFT. I'm not talking about all of this. And so this is a very nice example. So we show that if you use AIKM1, it correctly predicts the structure, polymeric structure. While DFT fails completely, it just predicts the same bond length. And surprisingly, is better than X-ray for some cases. Like this is an interesting molecule. It has triple bonds here. And triple bonds are underestimated by traditional X-ray, while we get the corrected bond length. Well, you can read it later in the paper, and here is one of the final points that AIKM1 is transferable. So it can be applied to charged species, not as good as for neutral species, but it's kind of okay for many properties. Sometimes it's better than DFT with double zeta. And you can run geometry optimization with it better with some empirical methods. So It can be used for non-covalent interactions with accuracy comparable again to DFT. So, and it can be used for excited state calculation with accuracy again comparable to the TD-DFT. So there is really no excuse to not use this method and still stick to B631G star. You should use this method. This is another example, like you can do excited state geometry optimizations, which is slow.
Sorry, Pavlo, can you finish in 1 minute?
Okay. One of my last slides. And well, it's not always perfect, and it has still some limitations. It's only limited on a couple of elements that we optimized, but it covers organic molecules pretty well, and it can be still improved, but already has quite good accuracy for different properties. Well, with this, I would like to thank the people involved in collaborations in these works and my group members that helped to develop all these methods, and Pekundi this AIQM1 by himself with my input. Okay, thank you very much for your attention.